In the final session of this module, we will look at finite state machines, including event-driven programming, and then look into prototyping our system. The learning outcomes for today are that you will be able to apply an event-driven approach to your programming. You will be able to design and utilize finite state machines and state transition diagrams in the controller development of your mechatronic system. We will also look at what is required to take your simulation work into a working prototype, including how we transfer our developed programs from the simulator to actual implementation. Note the actual implementation will be on Tinkercad, although there is nothing stopping you copying this Tinkercad code onto an actual Arduino. In the first topic of today, we will look at how to implement event-driven programming, which then leads us on to representing our system as a finite state machine. The programming you have done up to now on this course was predominantly linear-based. By this, I mean that your program was written as a list of instructions, and you rightly expect your program to sequentially run through each line of code. By knowing the clock speed of the processor, you can also predict how long each section of code would take to run. Thus, the execution of our program runs in a linear fashion. The exception to this was when we looked at using interrupts to measure the speed of a driven wheel in the module instrumentation and drives. If you think back, when a signal was detected on the interrupt pin, the program left the main program code and instead executed a function to increase the value on our pulse count variable before returning to the main program. Thus, our program did not always run in a linear fashion. Sometimes it was interrupted by what we call an event happening. All programs will need to run to some extent in a linear way, namely start from the first line of code and then execute subsequent lines of code. However, in event-based programming, the lines of code are looking to see if events have occurred and then act on these events accordingly. Thus, the program flow is predominantly unpredictable, as it is responding to any events that may be happening during the time of program execution, which are in themselves unpredictable. Mechatronic systems require event-based programming to operate efficiently, as the system must react appropriately to their inputs. These inputs can occur in any order and at any time. For example, consider a washing machine. This may at first sight appear to be a linear process, in which the system waits for the start button to be pushed, the door is locked, water and soap enter the system, the motor spins slowly, water is drained, the motor spins quickly, water is drained again, the machine beeps to indicate end of cycle, the door unlocks. But this linear approach does not take account of any events that may occur during this washing cycle. For example, what if you press the pause button? What if the water is the wrong temperature? What if the clothes get trapped in the drum, thereby putting strain on the motor? You need event-based programming to be able to account for these occurrences. As another example, consider any graphical-based operating system, for example Windows. These use event-driven programming. For example, if you move the mouse pointer over an icon, the icon is highlighted. If you click the mouse button, then a specific action will take place, and similarly if you press a key on the keyboard. It is impractical to program such functionality in a linear fashion. The program has to react to these inputs as they happen. It is important to understand the terminology when we are talking about event-based programming. An event is an action that occurs, for example, someone turning on a light switch, a door closing, etc. It is important to note that this is an action and not what state something is in. For example, a light may be illuminated or not, namely it is in an on state or an off state. This state is not an event. However, switching the light on or off, namely changing it from one state to another, is an event. Thus, when we are recognizing an event, it is this switching or change in state process that we are looking for. When an event occurs, we will want our mechatronic system to react accordingly. We do this by writing a service routine, namely a piece of code or program function to get our system to react to this event. An example of this is our interrupt service routine in the instrumentation and drives module, in which we wrote a small piece of code to count the number of pulses when an event was triggered on the interrupt pin. It is very important to keep our service routines as short and quick as possible, because when they are running, they are not looking out for other events that may be occurring. Blocking code refers to program code that stops the program from executing other code. For example, if you wrote a while loop which contained code that waited for a key to be pressed, then the program would do nothing else but wait for that key to be pressed before any other code is executed. Thus, this piece of code would be blocking any other code to run at this time, with the exception of an interrupt routine. It would be better to write this key press recognition as an event, and have the code look out for this event rather than wait for it. All code, to some extent, is blocking. However, we use the term blocking code to indicate a possible significant delay in program execution. Take the pulsing command for reading an ultrasonic sensor. When you initiate this command, the code sends out a trigger signal to the ultrasonic sensor. The sensor sends out an acoustic pulse. Depending on the distance to the object, there will be a time delay before the echo is received. The sensor indicates a received signal on the echo pin, which the program code reads and works out the time taken. Whilst all of this is going on, your main program code is held at this pulsing command until the signal is returned. The pulsing command has thus blocked any other code from being executed. So should we not use the pulsing command? It depends on your application. You may find this delay is acceptable and does not affect operation of your mechatronic system. Therefore, there is no harm in using it. However, what if this does cause a problem? One option would be to code this ultrasonic sensor reading yourself as an event. For example, you can get the current time and initiate the trigger. You then run the rest of your program code as normal. The echo signal is attached to an interrupt, so as soon as it is received, you can service this event by getting the current time again, and subtracting from it the time the sensor was triggered. Thus, you have coded the same functionality as the pulsing command, but you have not blocked the rest of the program code from running. I am not wanting you to totally eliminate blocking code from your programs. This is impossible, but you need to be aware of it. If it affects system functionality, try to minimize it as much as possible. When using event-driven programming, we need the program to look for events as they happen. This will typically be an input from a sensor, a user interface command, or possibly a signal from the clock oscillator if a timing event is required. It is impossible to try and time your program code to coincide with these events occurring, and therefore we would typically require an interrupt to recognize these events. Each processor will come with its own unique set of interrupts. For the Arduino, there are several options. The standard hardware interrupt is what we used for wheel speed measurements in the instrumentation and drives module. In this, we allocated pin 2 as an interrupt pin, and when a rising or falling edge was triggered on this pin, the appropriate interrupt service routine was executed. The Arduino Uno has 2 interrupt pins, these being digital pins 2 and 3. These can be triggered on a rising or falling edge, by a change in state, or by when the pin is low, the latter being a state rather than an event. The Arduino Mega has 6 interrupt pins, these being pins 2, 3, and 18 to 21, although with limitations. The pin change interrupt on an Uno is different from the hardware interrupt. In this, you can use most of the available pins as interrupts. However, these interrupts are allocated as ports, port B being assigned to digital pins 8 to 13, port C to the analog pins A0 to 5, and port D to digital pins 0 to 7. Only a change in state can be detected on the whole port, and it takes additional programming to identify which pin within the port was interrupted. The timer interrupt utilizes the internal clock oscillator. The oscillator's base frequency is 16 MHz, but the timers can be set to multiple values of this. For example, a count can be every oscillation, or every 2 oscillations, or every 4 oscillations, etc. If you count these pulses, you can trigger an interrupt when the counter reaches its limit, known as overflow mode, or when it has reached a certain value, known as compare-match mode. The latter is a very good way of ensuring precise timing in your applications, for example the signal needed to control a servo motor. Interrupts are great for recognizing an event, but we may not need, or even want, to instantly do something when an event is triggered, and more importantly, not have the option to use an interrupt. Any microcontroller has a limited number of interrupts, and so we may need another option for detecting events. We can program our code to look to see if information is available. This is known as polling, in which the microcontroller is asking the sensor or other piece of hardware for information. Compare this to an interrupt, in which the external hardware is telling the microcontroller information is available. We do not want our program to wait for this external hardware to supply information. This would be blocking code and would significantly affect our program execution. However, we could, for example, get our hardware to indicate if a message was available. As an example, consider we have an array of data which our sensor needs to send to the microcontroller, although we do not know when this data message will be ready. We could program the external hardware to set a digital pin on our Arduino to high if the message was ready to send. Our Arduino program could then check if this digital pin was high, and if so, our service routine would then read the message. Thus, we have not wasted any time waiting for the hardware to collect the data. If this message was of high importance, namely we needed it as soon as it was available, then we could attach this message available pin as an interrupt. However, we are more likely to just want this information within the next loop of program execution, and so we can have this message available pin as a standard digital input pin that we can poll in our program. In some cases, we can also recognize an event by measuring a change in state. For example, if we have recorded a switch as being off and then poll that switch in the next program loop, if that pin is now on, then we know an event has occurred. If this application was, for example, the pause button on a washing machine, then it is acceptable to use this polling approach to wait for the next program loop to pause the wash cycle. However, if this switch was a collision bumper on our robot, we may wish to attach it as an interrupt, so the event is immediately acted upon. As you can see, there are lots of options available, and it depends on the urgency of the information and subsequent action as to what approach is the most appropriate. Event-driven programming is a great option when your system has to react to unpredictable and non-sequential events. However, what if the action required for an event depends on the current state of the system? Consider, for example, a lift. You are on floor 1 and you want to go to floor 3, so you press the up button. The service routine on the controller would command the lift to go to floor 1 and open the doors. But what if the lift is on floor 2 taking a person to the ground floor? It will not want to stop at the first floor and take you to the ground floor first. However, if it is already on the ground floor, then it is acceptable to stop at floor 1 to collect you as it travels upwards. As you can see, once you have pressed the up button, it depends on the current state of the lift as to what action it should perform. Programming all of this information in will take a lot of if statements and can get very confusing, making it easy to make mistakes, and very difficult to debug the code if an error occurs. Finite state machines are a way to represent the possible states a system can be in, and how the system can move from one state to another. The moving between states is a transition driven by an event, and so event-driven programming can be utilized in this representation. This approach offers a highly visible viewpoint for how your system will operate, making it easy to develop, debug, and implement your controller. A finite state machine is represented by a finite state diagram. This clearly shows what different states a system can be in, and how it can change from one state to another. The two principal components of a state transition diagram are circles, which indicate what state the system is in, and arrows which represent from between which states the system can move, and in which direction. The arrows, known as transitions, are written as a numerator, which indicates what event has taken place, possibly a guard, written in brackets, this being a condition that must be met for the transition to occur, and a denominator which shows you any action which must occur due to this transition. The robotic cockroach example from Introduction to Mechatronics Design by Carrier is a good simple example of such a finite state diagram. In this example, if the cockroach is currently in a backing up phase due to a collision, it will stay in this state unless one of two events occurs. If it hits another object whilst backing up, it will move to an evade forward phase. If no other collision occurs, it will keep backing up until the timer expires. At this point, the timer expired event will trigger a jump. This will be to either the hiding state where the action is to stop moving, or to the drive forward state with the motors actuated. The decision on which of these states the cockroach goes into depends on the guard state, whether the light is on or off. We will work through an example of how to produce a finite state diagram and corresponding code by considering an example. The example is taken from Chapter 5 of Introduction to Mechatronics Design. Imagine you have a digital combination lock in which you must enter 3 digits in the correct order to open the lock. If a wrong digit is entered, the process of entering numbers needs to restart. If all 3 numbers are entered correctly, the lock will unlock itself, allowing you access to whatever is being held. When you wish to relock this, you can either mechanically close the lock, which will reset the number entry, or you can just type in a random number to reset it. Our finite state diagram consists of 4 states. These are either no correct numbers, 1 correct number entered, 2 correct numbers entered, and all 3 numbers entered. The last state corresponds to the lock being open, so we'll label the 3 correct number cases open. As you can see in our FSD, we have got 4 circles, each corresponding to one of our possible states. Next, we need to consider how we move between states. A correct number will transition us to the next stage if it is correct, or take us back to the starting point if incorrect. An incorrect number at the beginning just loops us back around to the same state as we are still at the beginning. Once the lock is open, we have 2 possible transitions to get us back to our starting locked position. This is a very simple example, but allows you to see how we can produce a finite state diagram. Our previous robotic cockroach example is slightly more complex, and depending on your system, your finite state diagram may have many more possible states and corresponding transitions. However, in all cases, this diagram allows the designer to easily visualize all possible scenarios for the event-driven system. Our finite state diagram consists of a series of state and transitions. To code this, we could use a series of if statements. This is feasible for a simple FSD, but as your FSD becomes more complex, the if-else if-end approach becomes impractical. A much better option is to use the switch case control structure. In this, the program is informed to switch the program execution to one of its following cases, or options. Each case is labeled as an option for the variable being considered. The code for that particular case will be executed, and then the break command will take the program execution to the end of the switch command. If no cases correspond to the variable, the default statement is implemented. For our digital combination lock example, the program code will look something like this. Note: I am not wanting you to concentrate on the specifics of the code. For example, what is the check keys function? I want you to concentrate on the program structure and the principles of coding this way. This part of the code is the main program. You can see that the program just runs in an infinite loop with the while one statement. Within this loop, all the program does is check for an event, i.e. it is event-based programming. On registering an event, the if statement, which is only true if a key is pressed, is activated, which calls the service routine. This is the service routine. Note I've had to split it into 2 columns so you can see the complete structure. The lock exists in a current state which is initialized as none right at the beginning. This current state variable is assigned as static. This means that it will remember what the value was from the last time this function was called, and it will use this previous value. It will not reinitialize when the function is recalled. The code then consists of a series of switch case statements. The first switch command will take the program execution to the point of code that corresponds to the state that the lock is currently in. The switch command within this case then decides on what action to perform by considering what event, or key press, has taken place. This transition to a new state is then saved for the next time this routine is called. Take some time to have a look at this structure to see how it works. There are two important points to note from this. Firstly, the control process was designed at the finite state diagram phase and not the coding phase. This has made it very clear for you to see what states and transitions are required, and it is much easier to program what you need. Secondly, the code for each case is very simple, albeit there are quite a few cases to consider. This makes writing and debugging the code much simpler, as you can easily check each small piece of coding for each case, rather than look through an entire, and possibly complex, complete program. In the next video, we will look at electrical schematics.